Today, we'll be talking about Bernoulli's equation, which is an important concept in fluid mechanics. So what Bernoulli's equation states is that along a streamline, the sum of all of the pressure, which includes static pressure, hydrostatic pressure, and dynamic pressure, is constant along a streamline. And this can be modeled using Bernoulli's equation right here, which includes a static pressure term, a hydrostatic pressure term, and a dynamic pressure term. And the sum of all of these will equal some constant pressure along the streamline. An important note is that Bernoulli's equation uses gauge, not atmospheric pressure. So whenever you're working with Bernoulli's equation, make sure you're using gauge pressures. So some notes about Bernoulli's equation is that it cannot be applied across pumps or other systems that supply or use energy. If you're working with a pump or a turbine or something like that, you're going to be using a conservation of energy equation, which will come later. But with Bernoulli's, we're not going to be applying it across pumps or other systems that supply or use energy. Some general assumptions for Bernoulli's equation is that it's steady flow, incompressible, inviscid, and irrotational. Here's our example problem. So this pump shown creates a water flow in the pipe such that the velocity is 14 meters per second, right here. And they want to know the pressure at the gauge, which is, I guess, essentially the pressure right here. So let's talk through how to solve this using Bernoulli's equation. So the steps of this are first to select points of interest, choose a streamline, establish a datum, write Bernoulli's equation from one point on the streamline to another on the same streamline, and then solve for the unknowns. So when choosing points of interest, go ahead and pause here and look at some tips to select these points of interest. So essentially, we want to make sure that we're choosing points that can help us solve the problem, that'll help us cancel terms in Bernoulli's equation, and where there's a lot of terms in Bernoulli's equation that are already known at those certain points. So points of interest that can help cancel out terms in the equation include points on the surface, because that would mean that the static pressure is 0. Points in a large tank, which would mean that the velocity is 0, since by the large tank assumption, the fluid's not really moving. Points on the datum or the reference line, because that would mean that our Z term for hydrostatic pressure would be 0, so that term would cancel. And then points at the maximum height of a jet stream, because if we're at the peak height, the velocity is 0, according to derivative rules. So for this example problem, let's try selecting points of interest. So pause the video and try to select 3 points of interest. The points that I've chosen are points A, B, and G. Next up, you want to choose a streamline. And when you're creating a streamline, you want to just connect all of your points of interest without passing through a pump or any other energy supplying or absorbing systems. So go ahead and pause the video and try to draw the streamline. I kept it simple and I just connected B, A, and G without crossing over that pump. Next, you want to establish a datum, which is essentially a reference line. So you want to establish this datum in a location where Z can be calculated for all points of interest and or Z equals 0 for one or more points, because that would then allow you to cancel the hydrostatic pressure term in the equation, since Z would equal 0. So now we're going to work on establishing the datum. So pause this video and establish the datum. There's multiple options here. I chose to establish my datum going straight through points A and G, since we see that this distance right here, the 4 meters is known. So now we know ZB is 4 meters, and it seems that Z for A and G are both 0. So we get to cancel out that hydrostatic pressure term for points A and G. Next, we want to write Bernoulli's equation from one point on the streamline to another point on the same streamline. So I actually recommend writing Bernoulli's equation for each point of interest as one long set of equations, all set equal to each other, since we know that the total pressure is constant along the streamline. So for this example problem, let's go ahead and work on writing our equation. So pause this video and write Bernoulli's equation between points A, B, and G. So I have my equation written right here in purple, just connecting Bernoulli's equation at A, at B, and at G, all set equal to some constant total pressure. Next, we're going to try to solve Bernoulli's equation. So what this means is we're going to cancel out any 0 values with justification, plug in known values, and then solve for our unknowns. Go ahead and pause the video and cancel out your variables using your assumptions. And go ahead and pause the video again and see if you made the same assumptions that I did. So the justifications are all written in yellow here. Now pause the video and simplify the equation, which means just get rid of the 0 terms. So I have it written in blue. All I did was just omit the terms that were equal to 0 based on our assumptions. Now pause this video and write down any known values that you could use in this simplified Bernoulli's equation. And I have my known values listed up here that I got just by looking at the figure. We got ZB from this distance. Our velocity was given in the problem, and our specific weight of water and our density of water are in your properties tables for your fluids class. Now go ahead and pause the video again and plug in your known values to your Bernoulli's equation. Then I went ahead and in green, I plugged in all of our known values into our equation. And we know that PG is our variable of interest because it wants to know the pressure at the gauge, and our point G is the point that's located right at the gauge. So we know that we're solving for the pressure at G, so that PG variable. So I want you to pause the video and solve for PG. So when I was solving for PG, I chose to just use Bernoulli's equation between B and G, since these two equations have the most known values. PA wouldn't really help us, so I'm not worried about using Bernoulli's equation there. But I went ahead and I solved for PG, and I got a total pressure at the gauge to be negative 58.5 kilopascals. So that's our final answer. And just like that, that's it for Bernoulli. Thank you for watching, and I hope this helped.